In this lecture, we will continue the discussion of Bode plot, and we will see that how to uh, plot the magnitude of given transfer function and phase of the given transfer function in quite approximate way using this Bode plot technique. So in the last class, we had pointed out all these steps required for uh, making Bode plot. So first step was to factorize the given transfer function in terms of simpler terms. For example, here we are doing with the first order terms only, and then convert it into standard form. That means the constant term here should be 1, and then convert S into j omega form, and in the fourth step, we represent this transfer function in dB scale so that this division and the product between various factors, this gets converted into subtraction and addition. So if we do that, what we will get is transfer function as sum or difference of simpler terms. So if we plot each of these four curves, the overall curve will be simply addition of these. For remaining two, last these two, we will have to do the subtraction. So there is also addition with negative sign of the curve. So that is the advantage of going for the dB scale. And similarly, when we talk about the phase of the transfer function, in that case also, the phase simply becomes the sum of the individual phase. So now we will see what are the Bode plot for each of the terms. For example, here what we have is a constant term and first order term without any additional constant, and then first order term with constant present. So if we know the Bode plot of each of these types of three types of curve, then we can simply add them to get the overall plot. So let us start with the so this is the step 4, and let me complete this step by pointing out that step 5 is simply the plot individual terms rather of the transfer function, and add them to get the complete Bode magnitude or page plot. So now we will see the Bode plot of each of those individual terms so that we can make the complete plot of any given transfer function. So first case, let us take a very trivial thing that we have constant term. That means k dash, what we got earlier. So for this case, we saw that this will contribute 20 log k dash, and its a plot is going to be a constant number Here we have omega in log axis, right? Now we take, so for this case, we can do the phase plot also. So phase of k dash, we know that is 0 degree. So if you do the phase plot, this is simply going to be like this. Now case 2. So here we have a term like S, that means this is equivalent to j omega. So if we have this type of term, then what will be the magnitude and phase plot? So when we go into log axis domain, then we have 20 log mod j omega, and here this is 20 log omega. And what we are doing, so we will say that we have a transfer function which is of this form. So here we have 20 log h j omega magnitude is equal to this thing ultimately, 20 log mod omega, or simply omega also. So here you can see that this is y-axis and x-axis is always log omega. So this becomes 20x. So if we have a transfer function like this, and this will also be called as 0 at origin. That means when frequency is 0, that time the transfer function is 0. So for this case, the Bode plot is going to be a straight line with slope 20 dB per decade. Right. And for this transfer function, or for this factor, we can see what will be the phase. So h j omega is j omega. So phase of h j omega becomes phase of j omega, and then we know that this is equal to uh, pi by 2, right? So the phase plot for S term, you can say, is like this, 90 degree. So here we have a first order term without any constant added here. No constant is present here. So we can now, and this is 0 at the origin. Similarly, there will be a pole at the origin. So we can have this scenario 1 by S, which is present in the example that we started with. So in this case, you can see that the transfer function j omega is going to 1 by j omega, and when we go to log axis, this becomes minus 20 log j omega, equal to minus 20 log omega, right? So once again here we have y and this is x, so this can be written as y is equal to minus 20x, right? So we once again have a straight line passing through origin. So this is origin, and actually this is omega is equal to 1, but in log axis, because x-axis is log, so this is omega is equal to 1. So in this case, the curve will pass through origin, but now slope is negative. So here we say that there will be slope of minus 20 dB per decade. So when the frequency changes by 10 times, the Y value will decrease by 20 dB. So what we conclude is 0 at origin implies line from origin with slope plus 20 dB per decade. However, when we have pole at origin, this implies line from origin with slope minus 20 dB per decade. Right. So this is a distinction. And now if we see the phase plot, for this pole at origin, so here what will be phase of 1 minus phase of j omega. So phase of 1 is 0, and phase of j omega we have already found out is pi by 2. So the phase is minus pi by 2. So a 0 gives rise to phase pi by 2, and the pole at origin gives rise to phase minus 90 degree. So these are the individual building blocks or individual curves that we should know, so that we can combine them to find out the transfer function or plot of the any given transfer function. So we have already seen a constant term and pole at origin and 0 at origin. Now let us take the most general case that we have encountered in the example that we started with. So that will be called as case of 0 not at origin. That means transfer function is of this form, s by z minus 1. So here you can see that 0 is at omega is equal to rather s is equal to z. So what will be Bode plot for this case? Now let me also point out that all the cases that we have considered up till now, in all these cases, both the phase and the magnitude plot, they are accurate. That means exact. So approximation will actually start from this case 3. So the plot that we will get for this will be approximate. It will not be exact. So we will first have to convert it into frequency, and then to log axis, here. So now we will have to plot this one. So because exact plot will be difficult, so we will do the approximate plot. And to arrive at the approximate plot, what we will do, we will consider few special cases of frequency. And for those special cases, we will try to see that what will be the plot, and then we will try to create the complete plot for this type of scenario. 0 at non-origin frequency. So here the various cases that we will consider is when frequency is equal to 0 or very small compared with Z. So we are basically considering this case. And the extreme case is going to be omega is equal to 0. So now when we have omega very, very small compared with 0, that means omega by Z is going to be very, very small compared with 1. So in this case, this term can be neglected and we can retain only 1. Right? So this can be neglected. So this 20 log h becomes approximately equal to 20 log magnitude of minus 1. And this we know is equal to 0. So what this says is that suppose this is our Z, then it says that when you are in this region where omega is very, very small compared with Z, so in this region what will happen is the Bode plot will be something like this. So this is your origin, right? So we have found out the plot for very small value of omega. Now the question will be that what will be the plot in these regions when omega is large compared with Z. So the second case that we are going to consider, so this was the first case, omega 0 or very small rather. So second scenario that we are going to consider is omega much, much greater than the 0, right? Very large omega. So for this case, we can see that omega by Z is going to be much, much greater than 1. And this will allow us to simplify the expression here. For this case, 20 log mod h j omega will get approximated to 20 log mod j omega by Z. Right. So this is 20 log omega by Z. So this can be expanded 20 log omega minus 20 log Z. So here this is y, and what we now get is this is x, so 20x, and this whole thing is c, right? So here we see that we once again get a curve of straight line, but now it will not be passing through origin, right? It will intersect the y-axis at c in the negative part, and so the plot for larger omega we can now plot here is going to be something like this. So this is omega much, much greater than Z region. So we have found out the plot for omega much, much greater than Z, and for region omega much less than z. So now question will arise, what will be the plot in this intermediate region? So this is where approximation will be involved. So what is done is that we extend these two plots, right? So we extend these two plots and allow them to intersect, and it will intersect at the location of 0. Why? Because you can see that the equation is this one. It is this one which has been plotted for omega much greater than z, and now here you can see that this equation for omega is equal to z gives you 20 log 1, which is equal to 0. So this curve, or this curve, when extended for smaller omega, it will intersect, it will pass through this z. So what we say is that if we have uh, this type of term here, this type of, so its approximate Bode plot is like this. And slope of this part we have already seen is plus 20. So this will be plus 20 dB per decade. So it will rise by plus 20 for 10-fold increment in the frequency. Now, if someone plots the actual curve for this case, then the actual plot is going to be something like this here. So what we see is that the actual curve and approximate curve, they are exact in the omega much less than z, and also exact in the omega much greater than z. Not only that, the approximate curve, they are tangent for omega much less than z and omega much greater than z, right? And we know that tangent for very small, very large or small values, extreme values, they are called asymptotes. So that is why the curve that we have plotted, this blue curve or red curve, is the asymptotic plot of the actual one. So this is the actual, and this red one is the Bode plot or Bode plot. Right. So there will be small amount of error in this region here near the 0. So the maximum error occurs here. But nevertheless, we are able to predict the trend or the nature of the this transfer function quite well. So this is about the magnitude plot. Now we can go for the page plot. So we have h j omega is equal to j omega z minus 1. So this will write minus 1 plus j omega by z. Right. So here also the phase is going to vary. So if you, in this case, we can in fact find out the exact phase. Phase of minus 1, in fact We can here find the complete one. Phase of minus 1 plus j omega by z. So this will be tan inverse j omega by z, and this minus 1. So this can be written minus tan inverse omega by z. So this is the phase. Now this curve will also be approximated. So for approximation, we will consider the same two cases of the omega with respect to z that we consider for the magnitude plot. So case 1, when omega is much less than z. So in this case, you can see that this is going to be approximately equal to minus tan inverse 0. That means 0. Now we consider the second case, that is omega much greater than z. So in this case, phase is approximately minus tan inverse infinity. So this will be minus pi by 2. Right. And in this case, we will also find out phase for one special frequency, that is when omega is equal to z. Fortunately, this can be easily found out. So in this case, phase is minus tan inverse 1. So this will be equal to minus pi by 4. That means 45 degree. So this is 90 degree. So here we have three frequencies for which we know the phase values. So how do we plot then phase plot? So here we have negative axis. All the values are in negative, so that is why we have shown it in downward direction. And this is omega. And so what we have found is phase is equal to 0 when omega is very small, and phase is equal to minus 90 degree when omega is very large. And for omega is equal to z, phase is equal to minus 45 degree. So we know these three values. So now a question arises, how do we do the plot in this intervening region? So there are two ways in which this approximation is done. One very crude approximation is that you extend this curve up to 0, both the curves, and then make the sudden transition from 0 to 90 degree. But this is going to be lead to a lot of errors, so we will not follow this. But in some of the cases, this can be done. Rather, what we will do, we will join these 2 points. This point and this point, which is not known. I mean, we still don't know what is this frequency. Similarly, we still don't know what is this frequency. So we will join them by straight line such that it passes through this point, omega is equal to z, for which angle is minus 45 degree. So the question arises, where do we start? Where do we take these 2 points? So thumb rule is that you take these points 10 times of the 0 or 1/10 of 0. So we take this as 10z and we take this point as z by 10. So we mark these 2 additional points and then we simply join these 2 curves passing from minus 45 degree. So approximate phase plot for this type of term is going to be like this. And if one tries to see the actual one. So the actual one will be something like this. So the actual one will give the exact value, or the approximate one will match with the exact value at this location of 0, and in very small frequency region and very large frequency region. Right. So this is the phase plot for 0, not at origin. Now one can ask what will be the Bode plot for pole case. That means we now have a factor like this. So we first go to frequency domain, then we go to log domain, and here we get minus 20 log this one. So here you can see that we have exactly same scenario as we had for the 0 case, 0 at omega is equal to z. But now only difference here is that we have this minus sign, right? So if you try to work out the complete plot of this, what will now change is only the slope, because it was this factor 20 which was responsible for the slope in region where omega is much greater than this factor, which was 0 earlier. Now this is a pole. This is called pole, right? So if you repeat the process that we did for 0 case, then what one will get is, suppose this is the pole location, then one will get approximate plot like this. The curve will be coinciding with y is equal to 0 till pole, and after this it will be a straight line passing from omega is equal to p with a slope now minus 20 dB because of this minus sign. So this is a magnitude plot for pole not at origin, pole located at certain non-zero frequency. Now what will be the phase plot for this type of term? So for phase, we take as phase of this one. So this is phase of 1 by j omega by p minus 1. So we now have both numerator and denominator term, right? So the phase will be now equal to phase of numerator, which is 1, minus phase of denominator, which is j omega by p minus 1. So this becomes 0 minus, and phase of this part we have already found out for the 0 case was minus tan inverse omega by p. Right? So this becomes tan inverse omega by p. So we can do the approximate plot. Now this time you can see that we have a plus here. So this time this is the transition point, and here we have say 90 degree and plus 45 degree, and we will have to mark these 2 points 10p and p by 10. So the phase plot is going to coincide with x-axis till p by 10, and it is going to be equal to pi by 2, 90 degree. After 10p and at p, this is going to be exactly equal to 45 degree. So we'll now join these 2 points by a straight line passing from 45 degree curve. Right. So this is the phase plot for pole at frequency other than origin. So now we know all these cases. So there's one more possibility here, that what we consider up till now was transfer function of this form or pole of this form. But it might so happen that we might have plus sign here. For example, we can have transfer function like this, s by z plus 1. So factor, after factorization, you might get a positive sign here. So this type of factor also might occur. So the question will arise if we get this type of pole and 0. So here you can see that 0 is at 0 is at negative frequency. Similarly, pole is also at negative frequency, but here 0 is located at a positive frequency, and pole is also located at a positive frequency. So if we have pole and 0 at negative frequency, then how the approximate plot of this transfer function is going to get modified. Right. So we can go back to this negative case and try to see that what will happen. So if you go for the magnitude plot here, so here we had negative sign, and now we are going to have positive sign. So let us try to put positive sign and see that where modification occurs. So when you have put positive sign here, you can see that this part, this remains as it is. So this part also remains as it is. That means we are still going to get a curve which will coincide with x-axis even for negative 0. Right. So now when we have negative 0, we can see that that plus 1 will get dropped out. So this will still be true here. So we will still be getting this thing, and we will still be getting this curve. That means even if we have negative 0, the plot, approximate plot, is going to be exactly same. Right? So here you can see that by looking at the magnitude plot of any uh, simple factor, you will never be able to say whether the 0 is at positive frequency or at negative frequency. So the sign of this 0 is going to have no effect on the magnitude plot. So this we concluded for this type of term. So now let us see what will be the effect on the phase plot of this type of term. So for phase plot, we are here. So now you can see that we are going to have a positive sign here. So this sign will get modified. This will become positive. This will become positive, right? So now we are going to get positive here, and this is now going to get modified to positive. So that means this part, this remains as it is. This positive sign will have no effect. But now this part is going to get modified because here we have positive now. So this become positive. So angle is now going to be pi by 2 plus pi by 2. Similarly, this is also going to get modified to plus. So this also becomes plus, right? And now we are going to get 45 degrees. So we see that phase plot is going to be completely modified. And what we will get now is a plot which will be in positive direction rather than negative one. So this is 0. This is 90 degree plus 90 degree. This is plus 45 degree. And this time the page plot is going to be like this, starting from z by 10 to 10z, passing from 45 degree like this. So whether pole is at positive frequency or negative frequency, that information can be extracted only by looking at the phase plot, not at the magnitude plot. Right? Similarly, if you see the pole at positive frequency, this becomes plus, this becomes plus, this sign becomes plus, and this sign becomes plus, but this will remain as it is because this is arising because of 1 by s by p plus 1 type of factor. So in this case, the plot will remain as it is, horizontal up to p and then minus 20 dB per decade. However, if you see the phase plot, there will be modification. So this is plus, and here this becomes plus. So this sign will now become negative. So this time the phase plot will get modified. So this is P, this is 10P, this is P by 10, and then we have plot 0 up to P by 10, and then minus 90 degree, minus 45 degree, this. Right. So this is what we will have to keep in mind, whether the pole is positive or negative. Now we can take one example to see that how to arrive at the complete Bode plot. So suppose we have transfer function Hs is equal to 5 into 10 raised power 4 s divided by s square plus 505s plus 2500. Suppose this is a transfer function and we want Bode plot. So what we have to do in the step 1, we have to factorize it. So we are now going to trace the various steps that we listed earlier. So we have to factorize. So numerator part is already easy, no need for factorization. So we have to factorize denominator, that is s square plus 505s plus 2500, and this you can do easily. This will turn out to be s plus 5 into s plus 500, right? So the transfer function after factorization is 5 into 10 raised power 4 s divided by s plus 5 s plus 500. Now in the step 2, we convert it into standard form. So for that, modify these two factors. We have to take 5 and 500 common. So here you can see that we have a pole at minus 5 and minus 500. So this will become 5 into 500 s by 5 plus 1 and s by 500 plus 1, and numerator is 5 into 10 raised power 4 s. Right. So here this will become finally 20 s divided by s by 5 plus 1 and s by 500 plus 1. So this is the standard form. Now from here we can start doing the Bode plot of individual terms, but of course we will have to take a small simple step, step 3, where we substitute s equal to j omega. So we move to frequency domain. J omega is equal to 20 j omega by 5 plus 1 and j omega by 500 plus 1. Step 4 is going to be lengthy and the most important step. Out of all these steps, you can see that step 1 could be difficult. There could be more complicated factorization involved, more number of factorization involved. 2 and 3, they are easy. Step 4 is also simpler but lengthy. Step 4. So in this case, we plot individual factors of the transfer function. So here we have 4 factors. $20, or you can say a constant, then 0 at origin, pole at negative frequency, and 500. Right, so each of these four factors, they have to be plotted. So now we plot each of them individually. So first, magnitude plot. So here we will have to mark all those important frequencies, which is 5 and then 500. And keep in mind, although those poles, they are negative, we do not show those things on the x-axis. We continue to show the positive frequencies here. Their effect, as was pointed out, will be visible on the phase plot. Right. So we are going to plot individual factors here. Right. So first is this constant here. So this constant will give rise to a horizontal line like this with value 20 log 20. Right. Then the second term is 0 at origin. Right. And we know that this will give rise to a straight line passing from omega is equal to 1 on the absolute axis, but omega log omega 0 from this origin, because this is log axis. So it will pass from here with slope is equal to, here we will represent this point as 1. This is log omega. So it will pass from here with a slope, and this will extend from minus infinity to plus infinity for log omega. The slope is going to be plus 20 dB per decade. So now we have to plot the pole, this one. So for that, we will plot a horizontal line coinciding with the x-axis up to 5, and then a line with slope minus 20 dB. So it is going to be like this. This is going to be minus 20 dB per decade. Similarly, for the second pole, horizontal line up to 500, and then a line with slope minus 20 dB per decade. So these are the four curves which we will have to add to get the overall. So now we start adding them from minus infinity, starting from here, and we will add them up to plus infinity. Right. So let us first try to add them at this point. So here what we see is that these two poles, 5 and 500 pole, they do not contribute anything. Their value is 0. And this 0 at origin, its value is 0. It is only this constant term which contributes equal to 20 log 20, right? So at this point, the overall curve is actually going to be equal to this one. This is the point. And when you go on the left side of this point, then you see that this 0 at origin, this is decreasing. So this will, and these two, they do not have any effect. Their contribution is 0. So we simply forget them, these two curves. And so on this side, the curve will be like this, because we have constant here, and this 0 at origin, it decreases below this value. So before on the left side of omega is equal to 1, we will have curve like this coming from minus infinity. Right. Now from this point up to omega is equal to 5, we see that these poles, they have no contribution, and the constant term continues to give this value. However, this curve, the 0 at origin, this will increase the value at the rate of 20 dB per decade. So from minus infinity up till omega is equal to 5, it is this 0 which contributes, and constant term has only shifted this value by 20 log 20. Now after this omega is equal to 5, you can see that the first pole, this pole will start having impact. So this will try to bring about a decrement of minus 20 dB for every tenfold increment in the frequency. However, this curve continues to increase the magnitude by plus 20 dB for every tenfold increase in the frequency. So you see that now this curve, the first pole and the 0 at the origin, they will start impacting each other. In fact, both will contribute about the same time, same amount, but in opposite direction. So what will happen? Their contribution will get nullified, and what you will get here is a horizontal line, right? So the curve will increment up to omega is equal to 5, and then it will become flat, because we have one pole and one 0, both contributing same amount for every tenfold increment of the frequency. And this will continue till omega is equal to 500. And after 500, you will see that there will be 3 curves. One is this 0 at origin with contribution of plus 20 dB, and then we have our older pole at 5 minus 20 dB contribution. Now this pole at 500, it starts contributing minus 20 dB for every tenfold increment in the frequency. So here what we get in this region, we get contribution of plus 20 dB from this one, and then contribution of minus 20 dB from this pole at 5, and then contribution of minus 20 dB from pole at 500. So we can see that there will be net decrement of minus 20 dB after this 500 frequency. So plot is going to be like this, minus 20 dB for every tenfold increase in the frequency, right? So this is the overall plot of the transfer function. Similarly, you can do the phase plot also. Make the phase plot of the individual factors. This constant, 0 at origin, pole at 5, pole at 500, and add them. So that will give the overall phase of the transfer function. So keep in mind, we have discussed only up to the factors of first order. In general, there could be factor of second order also, or equivalently factor, first order factor with complex pole and zero. So those parts we are not going to discuss. That will be covered in more detail in control theory classes. This will be enough for us